Welcome to your video tutorial for section 13.1, curves in space and their tangents. I am Dr. Simon Romero, and in this video tutorial we're going to talk about curves in space and their tangents. These are the topics that we're going to follow, and these are the practice problems. I suggest you to do them all. Definition of a vector function. A vector value function, also called a vector function, is a function whose domain is a set of real numbers and whose range is a set of vectors. In other words, we're saying that vector functions will have inputs, numbers, and the outputs are going to be vectors. Geometrically, what does it mean is that if we put the outputs of the vector function in standard position, the thing that we're going to do is, with different t's, the value of the vector of the vector function may change. And at the end, the thing that is going to happen is if we plot all the tips of the vectors in standard position, we obtain a curve in space. And the curve is going to be nice if it satisfies certain properties that we will see later on. Vector functions and components. Since every vector is defined by its components, vector functions are going to be defined by functions in each one of the components. And of course, these functions are going to be called the component functions. Notice that doing calculus in vector functions is going to be very easy, because the only thing that we're going to do is we're going to do calculus in each one of the component functions. Curves in space. Given a vector function r of t with the component functions, the space curve defined by r of t is a set of points x, y, and z such that x is equal to f of t, y is equal to g of t, and z is equal to h of t for the same value of t. And these equations are called the parametric equations of the curve. What we're saying here is all the points in the curve are going to be all the tips of the vectors once they are put in standard position. Sketching space curves. So here is an example of how do you sketch space curves. An easy way is just finding the parametric equations of the curve and then just plugging points for t. And I could do that, but I prefer to give you a better understanding of why the graph is the way it is, or how the sketch of the graph is the way it is. So it will be convenient if we can find a surface where this curve lies. And in order to do that, the thing that we're going to do is we're going to try to relate two of these three variables in this particular case. So let me just start with this. Now, notice that x and y have trigonometric functions, and we know a certain property about these trigonometric functions, that cosine squared plus sine squared is equal to 1. Now notice that here we have 4 as the coefficient of the cosine and the sine. So in other words, if we raise these to the square and these to the square, we obtain 16 cosine squared of t plus 16 sine squared of t is equal to 16. So that means that x squared plus y squared is equal to 16. Now if you remember, that denotes in space a circular cylinder. So now the curve is going to travel, or it's going to lie in this circular cylinder. Now how it's going to lie, that's where the c comes from. Well, if you take the x and y, that will give you a circular movement if you ignore the c. In other words, in the xy plane, that gives you a circular movement. Now what does the c does is it starts just raising or lowering according to the t the point. So for example, for these particular t's, the thing that's going to happen is going to raise every time more and more and more. So notice that the thing that you are going to obtain at the end is a spiral. Not only that, the spiral is going to have a very particular way of traveling that is going to be counterclockwise with respect to the z-axis. So this is the way that the computer generated version looks like. Notice that, so one of the points that I'm trying to make here is that every vector function is going to represent a particular way that you travel the curve. There could be a different vector function that represents the same curve, but it's going to travel clockwise instead of counterclockwise. And in other words, the spiral is you're going to travel the spiral going down. Parametrizing space curves. So now parametrizing is the act of finding vector functions, and I have like, I don't know why I have this extra off. Finding vector functions representing plane or space curves. So let's try to find the vector function described by the curve of intersection of the surfaces given there. So we're doing the inverse process. We start with a curve and we're trying to find the parametric equations and eventually the vector function. So suppose we have the cylinder here. So let's take the cylinder of radius 3. And here is the plane. Notice that this equation over here gives you a plane, and the curve of intersection is the intersection of the cylinder and the plane. So again, the key here is going to be the cylinder. Again, x squared plus y squared is equal to 9, and we know that cosine squared plus sine squared is equal to 1. So we're trying to figure out what x and what y can be with respect to x, with respect to t, in order to satisfy this equation. Notice that the only thing that we need to do is, instead of setting it equal to 1, we set it equal to 9. So you have 9 cosine squared plus 9 sine squared is equal to 9. And then from here we can say, well, one solution could be x is equal to cosine of t and y is equal to 3 sine of t. Could I have picked a different, could I have picked this as a y and this as an x? And the answer is yes. The only thing that is going to change is the way that you're traveling the curve. So finally, using the equation of the plane and solving, we get that c is equal to that. So these are the parametric equations, and the vector function is just putting each part of the parametric equations in the corresponding component, and you will obtain the vector function that we're trying to talk about. In particular, this vector function actually is going to travel the curve counterclockwise too. So it's going to travel more or less something like this. Limits and continuity of vector functions. So taking the limit of a vector function, as I told you, is pretty easy. Is just taking the limit of each component function. Continuity is going to mean that a function is continuous if the limit is equal to the value of the function. And what does it mean geometrically is that the space curve will be continuous too. Derivatives of vector functions. The derivative of a vector function is going to be defined as this, with limits. I should have used my marker, so with limits like this, but I wanted to stop at this one, where that's not the way that we're going to compute, but it's going to give us a good way of a good geometrical interpretation of the derivative that we're going to use later on. So you have r of t here, r of t plus h is there, and that vector over here is r of t plus h minus r of t. When you multiply by 1 over h, if h is really small, it will increase the length of the vector a little bit. And then when you take, as h goes to 0, this vector is getting closer and closer to be the tangent vector to the line at that particular point. So the derivative is going to give you a function that if you give me the t, I can tell you what is a tangent vector to the curve described by r of t. So let me just tell you a little bit about the derivatives and components. Taking the derivative of a vector function is just taking the derivative of the components. Taking the second derivative is just taking the derivative of the derivative, so it's going to be another vector function. Let me just tell you a little bit about finding parametric equations of the tangent line to the curve. One of the applications of differentiation in vector functions is finding the parametric equations of the tangent line. In order to find the parametric equations of the tangent line, we need two things: a vector in the same direction as the line and a point in the line. Note that the point in the line is already given, so we only need the tangent vector to the line at that particular point. Again, at that particular point, we have to find what parameter helps us. So we have to find the corresponding t that gives us the configuration 0, 2, and 1. So in other words, we set r of t equal to the vector 0, 2, and 1. So in this case, we obtain that t is equal to 1. Once we have t equal to 1, remember this is a very important step, because everything that we do with vector functions is going to be associated to the parameter t. So r prime of 1 is a tangent vector to the curve at point 0, 2, 1. Given that r prime is equal to that vector function, we have that r prime of 1 is equal to that single vector. Notice that this is a vector function, and 1 we plug in the t equal to 1, we obtain a single vector. That is the thing that we need in order to find the parametric equations of the tangent line. So at the end we obtain that these are the parametric equations of the tangent line. Differentiation rules, we're going to have some rules of differentiation, and all of them, I'm not going to go over all of them, but all of them are just going to be very similar to our normal differentiation rule. The derivative of the sum is the sum of the derivatives. You can take constants outside, and all of these are just product rules. So all of these are going to be product rules of the different combinations of vectors and scalar functions, or two vector functions with the dot product, or two vector functions with the cross product. And the last one is just the chain rule. Let me tell you, this example is a little bit more advanced, but this explains how powerful it is to do calculus with vector functions. Prove that if the magnitude of r of t is equal to k, then r of t and r prime of t are orthogonal for all t. We start with magnitude of r of t is equal to k. So the thing that we do is we raise it to the square, and notice that once we raise it to the square, we have the magnitude of r of t squared, that's equal to r of t dot r of t, remember, by the properties of the dot product. Now we take the derivative both sides. Taking the derivative both sides, I use the product rule in one side and equal to 0 in the other side. And notice that after simplifying, we have that r of prime of t times r of t is equal to 0, and that finishes the proof. Two things. First of all, a question that you can think on your own, and we can discuss it later when we are in class, is what does this statement that we just proved mean geometrically in 3 dimensions. And the other thing that I want to tell is, well, how do I realize that I have to raise to the square? And the reason is because we want to modify our starting equation in order to create a dot product. The easiest way, starting with magnitudes, to create dot products is raising magnitudes to the square, because then you obtain that the magnitude square is equal to the dot product of the vector dot itself. And this is all for this video tutorial. Have a nice day.